Hello and welcome to this episode of Thermonuclear Takes from Physical Attraction. In the last episode, we gave some context for some new discoveries in high energy physics. So head back and listen to that episode if you would like that context. But otherwise, here we go, let's start talking about these new results. So first off, I want to talk about the Muon G2 anomaly. So let's just summarise what this is for the uninitiated. In our episodes on particle physics, the Concealing a Hadron series, we talked about the fundamental particles of matter, leptons and baryons, and the three families that they could be divided into. You have electrons as the familiar fundamental leptons which help to make up atoms, alongside the nuclei of the atoms, and they of course have heavier cousins in the other families, the muon and the tau. So muons, although short-lived in the wild, are fundamental particles included in the standard model in that middle family of leptons in terms of mass. One of the aspects of these fundamental particles is that they have magnetic and electric fields associated with them. But the unfortunate thing here is that these fundamental particles are essentially quantum entities. We have a picture in our minds, perhaps, of fundamental particles as bouncing around in space like little billiard balls. So if you want to include magnetism with your calculations, you might start to imagine that maybe the particle is like a ball with a certain electrical charge, and that then that ball is spinning, which generates the magnetic field. That's a classical analogy to what's actually happening. It's not a perfect analogy by any stretch of the imagination. But in this picture, you treat the electromagnetics of the muon purely classically. That would give you an incorrect approximation, just as you would get how these particles move and collide wrong if you imagine that they really were billiard balls. Unfortunately, the contributions to the actual magnetic field for these charged particles are a lot more subtle than that, and much smaller contributions to that magnetic field come from several different parts of the standard model. If we were just dealing with classically spinning charged spheres, as the approximation would have it, the magnetic moment, called G, would be 2. Electromagnetism and the weak interaction, however, in reality, as well as the strong nuclear interaction, all of these contribute to the muon's magnetic moment. So you have the big contribution from electromagnetism, from its electrical charge, but also from the strong and weak interaction as well. Now there are quite lengthy theoretical calculations undertaken to determine precisely what this value, this magnetic moment, should be, and that determines the strength of the magnetic field around the muon. And indeed, there are quite complicated theoretical calculations which determine what the contributions from each of the fundamental forces should be. The standard model and the associated mathematics allows you to predict these for the electron, the muon, and the tau particles. This then is where we get back into the fundamental idea of the interplay between experiment and theory, because you can actually measure this thing. Experiments in the lab have produced muons many times. You can measure the muon's magnetic moment by sticking it in a very precisely known magnetic field, and measuring how its rotation frequency changes in that field as the interactive magnetic fields interact with each other. And that tells you how strongly the muon is coupling to the magnetic field. But like all such high-energy fare at the borderlines of known physics, we're talking about having to make extremely precise measurements here. The value of the muon magnetic moment, as best we know it from the most recent experiment, is 2.00233184122. Typically, because this is so close to 2, they will subtract 2 and divide by 2 to give you a quantity called the anomalous magnetic moment, i.e. how much the magnetic moment differs from a perfect 1 when you scale it down to that 1. So the anomalous magnetic moment from this latest experiment is 0.00116592.061. When this was measured for the electron and the tau particles, the magnetic moment was basically as close to prediction from theory as we could possibly get it. Or, I suppose more accurately, you could say that the uncertainty in the measurement of the magnetic moment was within the theoretical prediction, so we can't tell any difference from reality and theory. But in results dating back to 2006, the muon magnetic moment was seen to be slightly off. How slightly is slightly? Well, by one reckoning, the theoretical calculation at the time said that the anomalous moment was 0.00116592.089. And the measurement then said that it was 0.0011659180. So the differences that we're talking about here are in the 7th decimal place of this quantity, the 1 in a million, 1 in 10 million range for this quantity. And this quantity itself relates to a tiny, tiny magnetic field produced by a particle which, at rest if it's not moving around, lives for an average of 2.2 microseconds before decaying into other particles. So the simple fact of the ridiculous precision you need to spot this difference, a difference in a millionth of a tiny quantity, that for something that lives for a millionth of a second, that you can be sure that there is a difference. That sort of explains why this has been such a controversial result for so long, because the difference is so tiny, the quantity is so tiny, and measuring it precisely to this level of precision is hard too. And of course you can see the broader point that we were making earlier, that a lot of this fundamental experimental physics is now happening at the ridiculous limit of what it's practical for us to measure, much like the case that we talked about where we were talking about the direct detection of dark matter. In that episode we described how successive generations of experiments have eliminated more and more swaths of interaction cross-section and mass which the potential dark matter particles could have had, as the detectors got more and more sensitive. For the muon magnetic moment, the initial experiments in the 1960s had a sensitivity close to 4,300 parts per million for the muon moment. The Brookhaven result in 2006, which kicked off this controversy, has reduced this down to just 0.45 parts per million for the muon moment. And the new experimental results that we're describing today, which came out this year, have shaved this down a little further to 0.46 parts per million for the muon magnetic moment. By the way, measuring this, the way they do it at the moment with the currently used experiment, requires a 1.45 Tesla magnet, 30,000 times stronger than the Earth's natural magnetic field. And you need to know the field generated by that magnet to an incredible precision in order to reduce uncertainty around the measurement of the muon's moment. Otherwise, if there's uncertainty in the field that's interacting with the muon's magnetic moment, then you're doomed. So there's a really quite incredible engineering story behind this, as there always is with these high-energy physics experiments. When this was first discovered, and when this first came up as an issue in 2006, there were of course several different explanations for what might be going on. One explanation is that the theoretical calculation of the muon's magnetic moment, the anomalous magnetic moment, was wrong. In particular, the way that the strong interaction might contribute to the standard model prediction for the muon's G was not particularly well known. Of course, the other explanation is that the experiment is wrong. After all, we talked about how difficult this is to measure, how precise the difference is, the possibility of systematic or statistical uncertainties that haven't been corrected for yet. Whenever an experimental result comes out that's surprising like this, these are the first things that physicists think of, and there's a litany of lists of fascinating initial results that later turned out to be measurement errors. This sort of thing happens all the time. And for that reason, when something comes out that's really surprising and against a theory, physicists generally want independent lines of evidence, independent experimental setups to remeasure the phenomenon, to confirm and back up, insofar as possible, any result. And the third explanation for why this has happened, the one that gets the most attention, despite arguably being the least likely explanation, is that this discrepancy between the theory and the experiment is because of some previously unknown physics. For example, maybe there's another term that we should be adding on to the calculation for the muon's magnetic moment, or it's influenced by another force, or influenced by another factor, or perhaps the way that we calculate it is simply wrong. But then further questions arise. Would this mean that the families of particles are not quite as symmetrical as we once thought, but that there's something weird and special about the muon? If we could measure the tau or electron moments better, would we find out something special about those instead? Or is this a symmetry breaking between the two different flavours? And if this really is some evidence of some new theory of physics, some more fundamental truths poking out of the discrepancies in what we can all measure, well, what would that then mean? What would the new theory be? And what else could it influence? How else could we detect it? Part of me kind of likes the perverse idea that if the universe did have a creator, there's just some very, very, very imperceptibly slight tweaks to some of these various, apparently fundamental or calculable parameters that we can measure. That they've put something in that a civilization exploring physics wouldn't notice until they got really far into their investigations, and then it would bug people for decades to come. Like the idea that there's a fifth fundamental force of nature, but all it does is ever so slightly mess around with the muon's anomalous magnetic moment and does absolutely nothing else. That would be evidence that the creator of the universe has a rather dark and warped sense of humour and enjoys torturing humans with absurd and unanswerable problems, which I would contend does actually gel pretty well with everything else that we see around us on a day-to-day basis. But unfortunately, this is not the kind of theory that is rigorous enough to pass muster in a scientific journal, and so, like much else, it's just another punchline. It's worth saying, of course, that there are examples in the history of physics where very small, but very real and measurable effects did turn out to change our understanding on a much more fundamental level. As long as you're not travelling anywhere near the speed of light, relativistic corrections like time dilation and length contraction, which depend on your speed and direction of travel, these things are incredibly small and tough to measure. If you were just dealing with things in the macroscopic world that we deal with every day, and things around us, these things would be almost imperceptible. But these fundamental slight deviations from the predictions from the Newtonian theory demonstrate that the old theory is that corner, that approximate limit, of the newer and more general theory. So you can see why, of course, the people who are devoting huge amounts of resources to understanding why this number appears to be ever so slightly different in practice are keen to think that this might be one of those very subtle hints that the nature of reality is not quite what we thought it was. But of course you can also see why ruling out those other kinds of error is important. So now that we've brought up all of that context, we can talk about what actually happened in April. After another 15 years of experimenting, the G-2 collaboration at Fermilab, who have been trying to refine this measurement yet further, have made a pronouncement, and that's what caused all the media attention. So what did they find? Well, with the most accurate measurement yet, the discrepancy is still in place. In other words, it doesn't look like they can attribute the measurements that came before to experimental error. The sigma significance level of this is around 4.5, so the chances of seeing a pattern of results this anomalous by sheer chance, or coincidence, is estimated to be something less than 1 in 40,000 overall. 5 sigma is what you usually have to quote for something to be classed as a true and incontrovertible discovery, which we've decided can't have happened by chance. But these things are all a little bit subjective, right? If you want to look at it like a good Bayesian, then I guess how much weight you give to a particular observation should depend on what your priors are like. In other words, if you find evidence of something exactly where you were already expecting to find it for very good reasons, then you probably feel a lot better about saying that what you found is evidence of that something. When they found the Higgs, its specs were pretty close to what was expected, it had been an integral part of theory for decades, it was the precise thing they'd set out to find. So in some ways your evidence threshold to be persuaded of something might be lower in that case, because it would make sense to find it there. If you're looking for evidence into something totally unexpected, or further making the claim that this experimental result is so groundbreaking that it requires brand new physics to explain it when the old theory works so well for everything else, then you should probably set the bar for claiming a discovery or a revolution in fundamental physics a little bit higher even than the Higgs 5 sigma bar. In other words, what we have now is very convincing evidence that the original measurement was not in fact an error, and that there really is a true discrepancy between the original standard model calculation and the muons G magnetic moment. But is that the end of the saga? Not at all, of course not. On the same day in April that these results were announced, some theorists also announced that they thought they had come up with a correction to the theoretical calculation, which made it possible to reconcile those two numbers again. This using a brand new method for calculating the calculation from the strong force, which brought this estimate closer to the original Brookhaven result. Zoltan Fodor, one of the scientists who was involved, wrote an article for The Conversation about it, which is Googleable if you're interested in the details here. But the upshot is that perhaps the anomalous moment isn't quite as anomalous as we'd thought after all. So the battle is far from over, and indeed new experiments are now gearing up to narrow down the measurement of the muon's anomalous G to an even finer degree. The Nature article entitled A Moment for Muons put it like this. The prospects for further insight are looking good. A reduction of the hadronic uncertainties by a factor of 2 is considered a realistic outcome by the end of the experiment's operation. Moreover, an independent method for measuring the muon's anomalous magnetic moment will be possible at the Japan Proton Accelerator Research Complex, or JPARC, in Japan. Expected to start operations in 2025, the experiment will make use of an ultra-cold muon beam injected into a compact storage ring with a magnetic field of unprecedented quality. With the targeted precisions of below 0.07 parts per million at JPARC and 0.14 parts per million at the Muon G-2 experiment, we will finally learn to what extent the muon's anomalous magnetic moment is anomalous. End quote. As ever, especially in modern physics, there's rarely a single eureka moment where the whole script is flipped, even though people might want to think there is and hype up the fact that there might be. And these moments, when they do arrive, often really only become apparent in hindsight, when they can be contextualised and when we can see which results stand the test of time, and of course the test of more tests, and which results do not. The muon anomalous G then remains a bit of a mystery. You'll find people arguing that it is and isn't compatible with the standard model, depending on how it's calculated. And amongst those who suspect that it isn't, and that this is new physics, you'll also find no shortage of theoretical explanations that might potentially offer a clue as to why. But assuming that this is indeed a gap in the standard model that now needs changing, it's a bit mysterious and unclear as to what it might potentially point to, and it's also not entirely clear as to what direction you want to go to for further study of this. If you discover a new particle no one's found before, well, you can measure the properties of the particle, see how it interacts with others, all that sort of thing. But discovering something like this, a slight discrepancy in what you calculate to be the case, is much more difficult because the possible explanations are pretty boundless and the direction of immediate further study not clear. As if muons weren't already troublesome enough, there was another weird result involving muons that was announced from the LHC at a reasonably similar time. Quoting from the Nature article entitled "What's Next for Physics' Standard Model," we have this, quote, "Meanwhile, physicists have uncovered more hints that muons behave oddly. An experiment at the LHC called LHC-B has found tentative evidence that muons occur significantly less often than electrons as the breakdown products of certain heavier particles called B mesons. According to the standard model, muons are supposed to be identical to electrons in every way except for their mass, which is 207 times larger. As a consequence, B mesons should produce electrons and muons at rates that are nearly equal." So you can see here again that any sign of a lack of the beloved and predicted symmetry in the behaviour of different families of particles, in any way they're expected to behave, always gets people salivating. It might explain other things that are asymmetrical, after all, like maybe, for example, the fact that anything exists at all, aka the matter-antimatter asymmetry. Or it could be evidence that at higher energies, as physics gets more fundamental and forces unify, there are higher symmetries at work, which are broken at the relatively low energies and late times that we exist at. In other words, the universe conceptually was once a perfect sphere, and it's now a smashed orb that's broken into many jagged pieces of different sizes. And fitting them back together again is difficult, because some are nearly quarter-sphere sized while others are practically glass dust. Part of the problem physicists now have is the great number of theoretical explanations there could be for these phenomena. The issue again is that these are not things that you're really expecting to find. Physicists have a lot of their own pet theories, and there are no shortage of supersymmetry models as alternatives to the standard model, or things that you can derive the standard model from, I guess. But as far as I can see, and I admit this isn't really my area, there are so many of these potential theoretical models, each of which often requires extra particles that are as yet undiscovered. You can almost find one off the shelf which could be chosen to explain away any kind of arbitrary result in experimental high-energy physics that you might discover. And when that's the case, you start to worry about how convincing the evidence is that one of these theories is really the true theory, if there's enough theories out there that you could find a theory to fit the evidence. In that case, again, it's not like we have a perfectly valid, very popular alternative to the standard model that loads of people love, where everything is exactly the same except the muon's magnetic moment and B decay rate are a bit funny. And, if that was the case, if that was the alternative theory that a lot of people were advocating, that explained precisely these two phenomena, maybe we would have more of a leg to stand on when we're talking about how this changes physics. In fact, there has been something of a struggle, even with all the supersymmetric models that there are, to find SUSY models where both of these are simultaneously true, where we both have this weird magnetic moment and this weird B decay rate. And some of them then imply something different about the universe, like the amount of dark matter that it should have in it, that we can't reconcile with observations. So it feels a lot like we're shifting the problem to somewhere else again. I had a lot of sympathy with one of the physicists quoted by Nature who said that when it came to explaining these results, he thought it was, quote, grotesque to see all of these old, discarded supersymmetry models being reanimated in an ad hoc way to explain these results. I'm quite appalled by this procession of zombie SUSY models dragged out of their graves, said the physicist who was called Falkowski. I think it's worth allowing ourselves to speculate with the theorists just a little, even if they are a little bit guilty of this sort of intellectual necromancy. Because if you didn't, this kind of news and this kind of result would not be especially interesting beyond saying, well, something's definitely weird, but it still might be a mistake, or else just something we can't really explain yet. Which is actually the same story that we had way back in 2006 for these results, at least for the anomalous magnetic moment. So for the sake of that fun speculation, I will quote now from the Nature article by David Castelvecchi about some of the other theories which have been proposed as potential explanations for the unexplained phenomena. He writes, quote, "Some solutions exist that could miraculously fit both of these strange phenomena. One is the leptoquark, a hypothetical particle that could have the ability to transform a quark into either a muon or an electron, which are both examples of a lepton. Leptoquarks could resurrect an attempt made by physicists in the 1970s to achieve a grand unification of particle physics, showing that its three fundamental forces, strong, weak, and electromagnetic, are all aspects of the same force. Most of the grand unification schemes of that era failed experimental tests, and the surviving leptoquark models have become more complicated, but they still have their fans. Leptoquarks could solve another big mystery, why different families of particles have such different masses, says Gino Isidori, a theoretician at the University of Zurich in Switzerland. Apart from the leptoquark, there is one other major contender that might reconcile both the LHC-b and muon G-2 discrepancies. It is a particle called the Z' boson because of its similarity with the Z boson, which carries the weak force responsible for nuclear decay. It too could help to solve the mystery of the three families, says Ben Alanak, a theorist at Cambridge. We're building models where some of these features come out very naturally. You can understand these hierarchies, he says. He adds that both leptoquarks and the Z' boson have an advantage. They still have not been completely ruled out by the LHC, but the machines should ultimately see them when all of the data has been analysed, if they still exist. The LHC is currently undergoing an upgrade, and it will start to collide protons together again in April 2022. The coming deluge of data could strengthen the muon anomalies and perhaps provide hints of the long-sought new particles. Although some are saying that a proposed electron-positron collider, primarily designed to study properties of the Higgs boson, might be needed to address some of the LHC's blind spots. Meanwhile, beginning next year, the Muon G-2 collaboration will release further measurements. Once it's known more precisely, the size of the discrepancy between muon magnetism and theory could itself rule out some explanations and point towards others. Unless, that is, the discrepancies then disappear and the standard model wins again. A new calculation reported this month of the standard model's prediction for muon magnetism gave a value much closer to the experimental result. So far, those who have bet against the standard model have always lost, which makes physicists cautious. So one of them is quoted here saying, "We are, maybe, at the beginning of a new era." So that ends what they had to say about it. I want to close off our little section on how these physics stories come about and how they come through the news and how they cycle out of the news again by pointing out something that really came out from our cosmology series. And I think it's a point about a basic aspect of human psychology, really. We construct things into narratives after the fact. People do this in their own lives. Maybe you're in the process of doing it right now, identifying events and moments and factors that felt important or crucial, or maybe those that didn't feel so important at the time, and weaving them into a coherent story. The fact that we are so addicted to narrative, and maybe deep down terrified of what a world might be if it weren't governed by the comforting logic implied by a narrative, our ability to understand and explain things with these stories, that's probably a topic for another show, but it certainly comes up here. But often these narratives can only be constructed after the fact, when the dust has settled, when you can actually coherently construct the story. Ever felt a bit like you've been living through historical events for the past few years? Again, the process of trying to work out where different events and phenomena and moments fit into the narrative is constant, ongoing, and disputed. So it is with scientific developments in the evolution of scientific theories as well. We can see this very clearly in the cosmology series, when it came to the long-ranging disputes and battles that we've talked about, between those who pursued the steady-state model of the universe and the model of an expanding universe that began with a Big Bang. There was no single moment, no seminal paper, no brilliant experiment that comprehensively proved the issue one way or the other, and caused all of the partisans on one side of the debate to immediately shut up shop, admit they were incorrect, and subscribe to the new model. Instead, the gradual process by which theoretical and experimental evidence accumulated, to the point where the vast majority of scientists ascribe to a Big Bang theory, rather than triumphantly declaring it as incorrect on national radio as Hoyle did, well, this was a process that took decades to unfold, and indeed it has been said that the sciences only advance by the funerals of those who refuse to give up adhering to their old theories. Similarly with these new results, it is impossible to tell at the moment whether they will, in the long run, be viewed as chinks in the armour of something like the standard model or not, or whether they'll end up being included in some long-term retrospective of how physics evolved over the 21st century by the 22nd century version of someone like me. We can't tell, despite the hyperbole that you see in the headlines, whether these will just drift away as more anomalous results that hope to challenge the established theory, but ultimately failed in that aim. Everyone suspects that what we have now, in terms of theoretical physics, is incomplete. even though it is already remarkably effective at predicting most of the practical behaviours of matter and energy that we might care about. But as to the long-term significance of an apparent tiny deviation in the B particle decaying into muons or the muon's magnetic moment, it sadly, with my best historian's voice on, is much too early to tell. Thank you for listening to this episode of Physical Attraction. Remember, there are many ways you can support the show. You can find us on the web at physicspodcast.com. There you'll find the episode guide with all of our previous shows that you can listen to. Pick out something you like from the archives there and enjoy that. If any of those shows interest you, or you think they'll interest a friend, please do tell them about that. I really appreciate that. On the website, you'll also find the contact form. Any comments, questions, concerns, feedback, praise, all of that you can send to me. I really enjoy getting your emails. It's a highlight of doing this, and keep sending them, please. You can get in touch with us in other ways too. We're on Twitter, at PhysicsPod. There is the Science Podcasts group on Facebook. And of course, in terms of more plugs, there's always the Patreon, where you can get episodes earlier than anyone else. And the PayPal link is there for one-time donations if you want to support the show financially. But the best way to support us, as ever, is to review us on various platforms and tell other people to listen to the show. I rely on word of mouth to spread the word of this show. We're approaching 500,000 lifetime downloads, which is quite an amazing thing, and hopefully we'll get there in the next few months. I don't know if I'll be able to throw a party for that, but it would be nice to if we could. So thanks to everyone who has made that happen. Until next time then, please do, take care.
Thank you.